Hello, Akwaba to the Math Classroom. If you are new, kindly don't forget to subscribe, like, and share the video. And to my already subscribers, I'd say Aiko. In this lecture, we introduce a type of derivative called directional derivatives. And these directional derivatives enables us to find the rate of change of a function of two or more variables in any direction. So we find rate of change of a function of two or more variables in any direction. So that's the interesting part added. We knew what derivatives were. You've solved examples of derivatives. But now we are adding another function to it. And that is what? The direction aspect. You recall in a previous lesson that if you have a function that is z, which is a function of x and y, we can find the partial derivatives. So we can find f with respect to x at, now you are finding it at a certain point. So at x naught, y naught, we knew it was equal to the limits as h approaches 0. You had the function f of x naught plus h, y naught minus f, the function itself, divided by h. Then the partial derivative with respect to y, it's also equal to our limits as h approaches 0. We had f x naught, you have y naught plus h minus the function at x naught, y naught divided by h. And this represents what? The rate of change. So these are what? Rate of change. Rate of change of z in the x and y directions. That is in the directions of the unit vectors I and what? J. That is what it then was implies. So let's suppose that we know or we wish to find the rate of change. So let's say we want to find the rate of change of z at the point x naught, y naught in the direction of unit vector. Let's say unit vector it's u, which is equal to a b. So to do this, we consider a surface. So let's say I have a surface S. Then with this surface, you have the equation. This is your function. So now let's sketch dates. So if I sketch and I have a point, let's say this is my point, x naught, y naught. I have it moving in the x direction and it moves in the y direction as well. And this thing is u, a vector u. So this is what you have this angle to be theta. So the x direction you have cos theta, y sine theta. So let's say this is x, this is our y, and this is our origin. So our unit vector u, which is AB, is going to be equal to cos u sine u. So our unit vector in words, polar coordinates, in polar words, coordinates. So then, so we can find a plane that passes through a point in the direction of what u. So say you have a plane that passes a vertical plane. So I have a vertical plane that passes through P in the direction of what u. So you have, let's say, you have a vertical plane, and this vertical plane passes through the direction of u, whichever direction u is going. So u could be going in this direction or any direction. So then that point you are talking about P in 3 dimension will be x naught, y naught, and what z naught in 3 dimension. But in 2 dimension, you just have x naught and y naught for that. So that if I want to find the directional derivative, then we are saying that our directional derivative, now we want to define what our directional derivative is. So then the definition is that the directional derivative of a function which f at the points x naught, y naught in the direction of a unit vector u is then going to be defined as the function at x naught, y naught is going to be equal to the limits as h approaches 0. You have f x naught plus ha, y naught plus hb minus the function at the point x naught, y naught. And all this is divided by h if the limits exist. If our limits words exist. So then, with this definition, we can actually take practical words examples to solve, which we'll look at in our next lesson. So kindly don't forget to subscribe and click on the bell to receive notification anytime a new video is uploaded. Thank you.